So finding the equation between two or more planes. So this is where you've got two planes that intersect, and they will intersect along a line of points. And occasionally you may be asked to find the equation of that straight line. To be honest, I think it's more of an A2 further thing that they would ask. They've asked it on the A2 further papers, but just in case they sneak it into an A2 further paper, I'll show you. There's a couple of different approaches you could take. So one thing you could do is you could do the cross product of the normal vectors of these planes, which would find the direction vector of the line between them. But we're not going to do that. I think an easier way of doing it is basically just finding 2 points that are on the straight line between them, and then once you've got 2 points, you can find this equation of the straight line. Okay. So we've got 2 planes here in Cartesian form. They're working. To find 2 points that are on both of them, I'm just going to pick a coordinate for X or Y or Z. Okay, it doesn't really matter. So I'm going to pick Z equals 0, which turns these into a pair of simultaneous equations, which you can solve on your calculator, or you can solve them by. And then whatever values you get, that will be a point that's on both of those planes. Okay. So there will always be a point that's got Z equals 0 on both of these planes. And if you solve them, that'll give you the points on both. When you calculate a simultaneous equations, 2 unknowns, 3x minus 2y equals 6, x plus y is 4. They're not that nice, but okay. So we've got x is 2.8 and y is 1.2. So a point that's on both of them is 2.8, 1.2, 0. We can again do a similar thing. So we can pick another value for z. This time I'm going to pick z equals 1. You can pick it for x and y. And so now I get 3x minus 2. 3x minus 2y. If I put in the 1, so it's plus 1, and then I take that across, it's equal to 5. For x plus y minus 1, and if I add that 1 across, I get that's equal to 5. Solve these in your calculator again, so just change those numbers at the end. 5. It's a nice number this time. So x is 3 and y is 2. 4.321. It's on both of these planes, so it's on the line in between. Okay. Let me try and draw you a rubbish diagram. So here's the planes. Here's one plane. Here's another plane. Imagine this is 2 sheets of paper kind of crossing each other, and there's a line in between them, like this. We're finding the equation of this line. So what we've done is find 2 points on that line, and then we can find the equation between them. I've got 2 points, so I need the direction vector between these 2. So I'm going to subtract them. So 3, 2, 1. Take away 2.8. 0.20. Gives me this for the direction vector. You could times it all through by 5 or something to make a whole number if you really want to, but you don't have to. And then the equation of the line at the end, r equals the point that it goes through. So I'm going to choose 3, 2, 1 because it's nice numbers. Plus lambda times this direction vector. With all sorts of answers you can have. I don't think it's a straightforward thing to do, but if it does come up, hopefully a bit better prepared for it. Yes.
You always plug the values in for Z.
No, you could pick X or Y.
No.
Yeah, that's fine. I just picked Z. So this time I picked x is 0 and y is 0, so maybe let's all do x is 0 and y is 0, just so we end up with the same answer, rather than having a million different answers. So have a go at this question. So yeah, you can pick values for x or y or z. So I picked x and y at 0 in this case. You could have picked values for z equally and got points out as well. So we've got these points. You can use either of those points for the first point in your equation in line. You can subtract them either way around for the direction vector. You can do any multiple of that. So for this one, I've times these through by 5 to take them whole numbers. You can't do that with the point, but you can do it with the direction vector. Yes. The key point about this is that on your formula sheet, there is a formula for the distance between a point, which they've called alpha, beta, gamma, and a plane, which is in Cartesian form. They're called the components of the normal vector n1, n2, n3. Notice it's plus d equals 0. So if there was a number on the other side, we'd have to bring it across to sub it into the formula. And the formula is just there. So it's basically the dot product of your normal vector and your point plus your d value here. It's important that you get this correct, otherwise this will be negative on here and you get the wrong answer. And then it's over the magnitude of the normal vector. There's modular signs on the top just because it's a distance and it should be positive. Okay, but make sure you remember that that's there, because a lot of these shortest distance problems can be turned into a distance between a point and a plane. So we'll use this quite a lot. So just a quick calculation here to find the distance from this point 1 minus 1, 5 to this plane. We're just going to substitute values into the formula. So n1 is your normal vector, so that's 1. Alpha is your first coordinate, so that's 1. And then we've got n2, which is 2, times minus 1 from the point, and then plus n3, which is 2, times gamma, which is 5 from the point. Let's just sub all of those in.
Where's it like?
Just a modular sign.
Of the whole thing.
Yep. Now we need plus d, which we don't have from this form, because it's not equal to 0. You could convert it into Cartesian form if you want. I'm going to take this minus 6 across to make it plus 6, which tells me that my plus d is plus. Say that again. Yeah, it should be 2.
These just these ones. So it could be okay.
Over the magnitude of the normal vector squared, so n squared is 1 squared plus 2 squared plus 2 squared. Square root that. And then we're just going to type this into the calculator and see what we get. I don't have to put the modular signs in my calculator, I can just make it positive at the end. So 1 times 1 plus 2 times minus 1 plus 2 times 5 plus 6 all over root 1 squared plus 2 squared plus 2 squared. Gives you the shortest distance. There is a formula in your pack here for the distance from the origin to plane. I wouldn't learn it. It's just putting 0, 0, 0 into your formula, which most of the stuff ends up being 0. So if you want to find the distance from the origin to that plane, so all we're doing in here is putting in alpha, beta, gamma of 0, 0, 0. All of this stuff ends up disappearing, and you just end up with your value at the top. Not effect. So the distance of the origin from the plane, everything ends up being 0. You just get 6 on the top. It was a D, I changed it because we've used D for something else. It's an L now. So just sub that in, it's thick over 3. Now, the next type of distance we're going to do is the distance between 2 parallel planes. I am not going to use this formula. We're not going to do the. It's rubbish. What we're going to do instead is turn this into a distance between a point and a plane problem. Okay, because if I can find the distance between one point on one plane and the plane underneath it, that's the same as the distance between both of those planes. Okay. So we've got two parallel planes here. They've got the same normal vector, so they're parallel planes. And all I'm going to do is choose one of these. I'm going to choose the second one and just pick some x, y, and z values that I know will work in that equation. Okay. So if I pick x is 1, y is 0, z is 0, that works. Okay, the left-hand side is equal to 2. So literally just choosing one of your equation planes and just looking at it and thinking about what x, y, z values will work in there. So I picked that one because it was equal to 2 rather than 17, and I thought it'd be easier to find a point that it goes to. Okay. So now this is reduced down to a shortest distance between a point and a plane problem. Because all I'm doing is finding the distance between 1, 0, 0. And this plane here. So let's substitute it all into our formula. So my normal vector that I'm using for this one is 2 minus 3, 4. So n1 is 2, alpha is 1. n2 is minus 3, but then beta is 0. n3 is 4, but then gamma is 0. All this ends up being 0. Plus d. Now, if I take this 17 across, d is minus 17. So that's why you've got to be really careful. It's easy to get that d sign wrong. And then it's over n1 squared plus n2 squared plus n3 squared. So that's 2 squared plus 3 squared. Plus 4 squared. A lot of this ends up being 0. Let's type this into your calculator. 2 times 1, next bit 0, next bit 0, minus 17. And that's over root 2 squared plus 3 squared. It's 4 squared.
Good.
Yep. So make it positive because of the modular sign. So 15 root 29 over 2. It's 15 over root 29 really, but that's nice. Key part about this is distance between two parallel planes. You can turn it into a distance between a point and a plane and just use the formula. You don't have to remember another method.
Really? That's weird.
It does smell weird. I don't know. Similar thing here. So we've got two parallel planes. Their normals aren't the same, but they are multiples of each other. So again, these are two parallel planes. I'm going to turn them into Cartesian equation just because that's what the formula's got. It's easier to see a bit. This is 3x minus 4y plus z minus 8 equals 0. And this one is minus 6x plus 8y minus 2z minus 10 equals 0. Put them both equal to 0. You could choose either of these ones and pick some values for x, y, and z that will work. So if I have a look at this one, I could just pick x, z is 8 and x and y are 0. Or you could pick y is minus 2 and a 0. That'll work as well. So just any x, y, z values that work will be a point that goes. So now this is the shortest distance between a point and a plane. So we're going to use the formula again on this one. So our alpha, beta, gamma is 0, 0, 8. Our n is from this one, so it's minus 6, 8, minus 2. Let's stick all that in. So I've got n1 is minus 6 times 0 from your alpha. n2 is 8, but again, beta is 0. n3 is minus 2, and gamma is 8. And then it's plus d, which is minus 10. Yes, I do. Then we're doing root 6 squared plus 8 squared plus 2 squared underneath. Let's just type that into the calculator now. The first one and second one are 0, then I've got minus 2 times 8
And then minus 10. And underneath I've got 6 squared, 8 squared, plus 2 squared.
So root 26 over 2.